In this video, we shall be discussing about applying backtracking to Hamiltonian cycles. So what is a Hamiltonian cycle? If we are given with a graph with set of vertices represented as V and set of edges represented as E, and we consider it to be a connected graph with n number of vertices in it, then a Hamiltonian cycle is a round trip path along n edges of G that visit every vertex exactly once and it returns to its starting point. That is, in a given graph, you are going to start from one vertex called the source and visit all other vertices exactly once, such that you are not going to visit these vertices again and get back to the starting vertex. That is what we called it to be the source. So in this particular graph, in the first example, we can obtain Hamiltonian cycles as or by visiting vertex 1 to 2 and then 2 to 8 and then 8 to 7, then 7 to 6, 6 to 5, 5 to 4, from 4 to 3 and then from 3 to 1. So here if you observe, we have been traversing every vertex exactly once. This is one example of an Hamiltonian cycle for this given graph. There can still exist many more Hamiltonian cycles for the given graph. So we can also consider one more example there. Maybe we can go from 1 to 3, 3 to 4, 1 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and then 7 to 8, and then 8 to 2, and back from 2 to 1. So if you observe, we have visited all the vertices exactly once. Now consider the second example here. So if you observe the second example here, let us try to find out a Hamiltonian cycle in it. We start from vertex 1, we move from vertex 1 to 2 and then 2 to 3, 3 to 4, and once I visit vertex 4, I'll have to get back to vertex 2 and I'll be visiting vertex 2 for the second time. So which cannot happen in Hamiltonian cycle. So such an vertex, I call it to be articulation points. So if I have articulation points in the graph, then I cannot obtain Hamiltonian cycles. Similarly, if we have a graph like 1 to 2 followed by 3 and then a vertex 4 followed by, let me say, vertex 5 and vertex 6. In this case also, if you observe, I don't have any edge to get back from vertex 5 to vertex 6, or I don't have an edge to get back from vertex 6 to the starting point, that is vertex 1. So I mean to say that we cannot find Hamiltonian cycles in graphs that have pendant vertices in it. Please make a note, Hamiltonian cycles cannot be found in graphs which have pendant vertices as well as which have articulation points in it. So in other words, if a Hamiltonian cycle begins at some vertex V1 in the graph G and the vertices of graph G are visited in the order V1, V2 and so on till Vn plus 1, then the edges vi and vi plus 1 are in the edge set E, and vi are distinct except for v1 and vn plus 1, which are equal. That is, the first and the last vertex in the Hamiltonian cycle would be same. Traveling salesperson problem is also an example of finding out an Hamiltonian cycle. So now we look at backtracking algorithm that finds all Hamiltonian cycles in the graph. The graph may be directed or undirected, and the output should always be distinct cycles. Backtracking solution vector x1 to xn is defined so that xi represents the ith visited vertex of the proposed cycle. All we need to do is to determine how to compute the set of possible vertices xk if x1 till xk minus 1 have already been chosen. If k is equal to 1, then x1 can be any of the n vertices. To avoid printing the same cycles again and again, that is n number of times, we will require that x1 here is always set to 1. If k is ranging between 1 to n, then xk can be any vertex v that is distinct from x1, x2 and so on till xk minus 1, and v is connected by an edge back to its previous vertex, that is xk minus 1. So I mean to say that in this solution vector, all the vertices that we are going to visit are distinct, that is x1 is different from that of x2, x2 is different from that of x3. So this gives us a sequence of vertices that we are visiting in the graph, and when we make an entry of some vertex xi into the solution matrix or solution vector, then we also see that there is an edge existing between xk to xk minus 1. Right? I again repeat, all the values in this solution vector are always distinct, and we also check to say that there exists an edge from xk vertex to xk minus 1. So now let us look into the algorithm to find Hamiltonian cycle. So we have two bits to this algorithm. The first one is Hamiltonian of k, and the next bit is the other algorithm to find the next value. So this Hamiltonian of k is a recursive formulation of backtracking to find all Hamiltonian cycles of the graph. The input to this algorithm is the adjacency matrix of the graph. So we'll have to first fill in or form the adjacency matrix. This problem is started by first initializing the adjacency matrix and then setting the solution vector x from the position 2 to n to zeros. And x of 1 is always set to 1, and then we start executing Hamiltonian of 2. So we always set x of 1 is equal to 1 because we want to get distinctive cycles. So we fix the source to be vertex 1. So now this algorithm runs for infinite number of times, right? That is until unless a solution has been obtained. So initially we assign x of 2 to x of n to zeros, and then we make a call in this repeat loop. We make a call to function next value of k. So this next value of k is called in order to assign a legal next value to x of k, that is to find out the next available vertex that can be included into the Hamiltonian cycle. And in case if we are not able to find out the next vertex, then we will have to backtrack to its previous vertex, which is done by this statement: if x of k is equal to 0, then return, right? So for example, if I am computing Hamiltonian of 3, right, and then I find that I have no other vertex to reach after vertex 3, then h of 3 will yield me a value 0, wherein I'll have to backtrack to a function call that is Hamiltonian of 2, right? So please remember this statement: if x of k is equal to 0, then return is going to perform backtracking. And then in case if we have found out the next vertex, that is x of k, which is not equal to 0, then what we do is we need not have to perform backtracking. So we try to check if this next vertex k that we have found out is not the last vertex in the graph by making use of the condition if k is equal to n. So in case if the vertex that we have found out is the last vertex in the graph, then it means that we have already found a Hamiltonian cycle. So therefore we simply print the contents of our solution vector. Otherwise out, if we have not found, or if the vertex that we have found is not the last vertex, then we make a call to function Hamiltonian, but this time the argument would be k plus 1, that is the next vertex that is to be found out. Okay, so the next piece of algorithm here is next value. Okay, so what does this next value algorithm do? So it's going to find out a path of k minus 1 distinct vertices. If x of k is equal to 0, then no vertex has yet been assigned to x of k. After execution, x of k is assigned the next highest numbered vertex, which is not already appearing in the solution vector and is having an edge back to its previous vertex given by the column in the solution vector x of k minus 1. Otherwise, if x of k is equal to 0, That is, if you don't have a suitable vertex that can be visited, then the column would be set to 0. And if k becomes equal to n, it means that it is the last vertex in the graph. Then you need an additional edge from x of k, which is connected to x of 1, because it's a cycle. So repeat until is similar to that of our do while loop. So in this do while loop, the very first statement is initializing the values of the solution vector. So let us say we had made the call to Hamiltonian of 2. So here is our example graph. Let us say that this is our solution vector, which has first column, second column, third, fourth and fifth column. So as we have only 5 vertices in this given graph. So initially x of 1 we have already assumed it to be the source vertex, that is we always consider source vertex as 1, so we fix it to 1. And then Hamiltonian of 2. So the case value was 2. So coming here, x of 2 we are trying to find out. So x of 2 to x of n is initially set to 0. So x of k is 0. 0 plus 1 is 1. 1 mod n is 5. 5 plus 1 is 6. So it gives me a value . Okay, so we start from x of 2, which is equal to, as I had already told you, so x of 1 will be initialized to 1, x of 2 will be set to 2. So x of 2 is equal to x of 2, that is 0 plus 1 is 1. So 1 mod n plus 1, n number of vertices, n is equal to 5, 5 plus 1 is 6. So 1 mod 6, I'll get a value as 1 itself. So x of 2 was previously 0, now it becomes 1. And then I check to see if I have obtained the next vertex or not. So if x of k is equal to 0, then we say that there is no vertex and it returns back to the function called Hamiltonian algorithm, right? So now if x of k is equal to 0, x of 2 is equal to 1, which is not equal to 0, so we come to the next line. So here we try to find out if there is an edge between x of k minus 1 and x of k. So x of k minus 1 is vertex 1 and x of k is also vertex 1. So we do not have an edge from vertex 1 to vertex 1 itself. So therefore this statement becomes false. So we do not have an edge from 1 to 1. So the value becomes equal to 0. So therefore we get back to x of k. So this time x of 2 is equal to x of 2's current value is 1. So 1 plus 1 becomes 2. So 2 mod 5 plus 1 is 6. 2 mod 6 is 2. So the new value of x of 2 is now equal to 2. So now again, if x of k, that is x of 2 whose value is 2, is not equal to 0, so therefore this statement will not be executed, and we come to the next statement wherein we try to find out if there exists an edge from x of k minus 1 is vertex 1 to vertex 2 in the graph. So we have an edge from vertex 1 to vertex 2 in the graph. Then it says that there is an edge. So what we do is we enter into the body of the if statement, and here we check for the distinctiveness of the vertex. That is, we have already seen the constraints for the solution vector, wherein we say that every vertex must be visited exactly once, therefore they should be distinct. The vertices should be distinct. If same, then again we are going to break out. So here for j is equal to 1 to k minus 1, k is initially 2, so 2 minus 1 is also 1. So we are going to check to see that x of j's value is 1, x of j has an element 1 in it, which is equal to x of k. K's value is how much? 2. So x of 2 has a value 2 in it. So 1 equal to 2 is false. So therefore the vertices are distinct. So we do not execute this break statement. We come to the next line here. So if j, yes, before we come to this line again, then there will be an j plus plus. So j was previously 1, now j becomes equal to 2. So here after it, coming out of the for loop, when j is 2, then 2 is not less than 2 minus 1, so we come out of this for loop. If j's value has now become 2 and k's value was also 2, if j is equal to, that is k, that is 2 is equal to 2, then it means that the vertices were distinct. So in that case, you check the next set of conditions, that is, if the vertex k is less than the last vertex, right? That is, if vertex k is how much? Vertex, it is 2. 2 is less than, total number of vertices are 5, right? So 2 is less than 5, so it is not the last vertex. Therefore, we again move on to finding the next vertex. Or the condition could be, if this condition is false, that is 2 is less than n is false, and let's say k is equal to n, that is the vertex that we have found tends to be the last vertex in the graph, then we also check to see that in the adjacency matrix, do we have an edge from x of n, that is the last vertex, to x of 1, that is the first vertex in the solution vector, right? So if k is equal to n and g of x of n, there exists an edge from x of n to x of 1, it means that we have got an Hamiltonian cycle, and we simply print the result and come out of it. So printing result is done in the algorithm Hamiltonian. So once we are done with this next value algorithm, the control is going to jump back to Hamiltonian algorithm to a line wherein we are going to check to see if k is equal to n. So if this, when this condition becomes true, there we have a for loop in which we are simply going to write the list of vertices that we have already visited.